We're going inward, toward something far smaller than anything you've ever imagined. Something so tiny that even the idea of space itself starts to get weird. This journey takes us to the smallest possible distance that can exist in our universe, a scale where our understanding of physics just stops working. This distance is called the Planck length. Now, the Planck length isn't just really small. It's fundamentally small. Think of it as a cosmic boundary, a point of no return where space and time, as you and I know them, stop behaving in any familiar way. Below this scale, concepts like how far, or where is it, or even when is it, might not have an answer at all. You can't measure it with a ruler, see it under a microscope, or even feel it as you move through the world. And yet, many physicists believe it might be one of the most important numbers in all of science. It's the place where our two greatest theories of reality finally meet, and they do not get along. On one side, you have quantum mechanics, the strange and wonderful set of rules that governs the tiny world of particles. On the other, you have general relativity, Einstein's epic theory of gravity, space, and time on the grandest cosmic scales. But when you try to apply them both at the Planck length, they give you conflicting answers. It's like two different instruction manuals for the same universe. And at this one tiny point, the instructions contradict each other. Understanding this tiny distance, this fundamental pixel of reality, changes everything we think we know about what the universe is actually made of. Our brains are wired for everyday scales. You're probably between 1 and 2 meters tall. You pick up objects measured in centimeters. Let's start our journey. The smallest thing your eyes can see without any help is about 1/10 of a millimeter. That's roughly the width of a human hair. Anything smaller than that is invisible to us. And this is where the story gets interesting, because it's where microscopes enter the picture. Back in the late 1600s, a Dutch scientist named Antony van Leeuwenhoek peered through his homemade lenses and discovered a completely new world. In a single drop of pond water, he saw tiny creatures swimming around bacteria and single-celled organisms. These little life forms were about 1 micrometer in size, which is 1/millionth of a meter. This was a revolution. If a whole ecosystem could exist at that tiny scale, what else might be hiding even deeper down? As science marched on, our tools got better. Microscopes improved, and researchers discovered that all living things are made of cells. Every step we took downward, we found more complexity, not less. But there was a limit to how far we could go this way. It's like trying to feel the shape of a tiny pebble with a giant beach ball. The visible light we see has a wavelength of about 400 to 700 nanometers. So, anything smaller than that is just a blur. That barrier held for a while, until the 20th century brought us the electron microscope. But their wavelengths can be much, much shorter than visible light. This new tool allowed scientists to push past the light barrier and see things down to the nanometer scale. Suddenly, huge molecules and even viruses popped into view. At this level, you can almost see chemistry happening. Everything you see, touch, and are made of is built from atoms. A typical atom is about 1/10 of a nanometer across. To give you some perspective, if you lined up 10 billion atoms side by side, that line would only be about 1 meter long. For most of human history, atoms were just an idea. It was a brilliant idea, but for over 2,000 years, it was just a philosophical debate. It was until the early 20th century that a series of clever experiments finally proved that atoms were real. At the heart of every atom lies a nucleus, a superdense core that contains almost all of the atom's mass. To picture this, imagine an atom is the size of a giant football stadium. The nucleus would be like a single grain of sand sitting on the 50-yard line. The rest of the atom, where the electrons are, is almost entirely empty space. Protons and neutrons are each made of 3 even smaller particles called quarks, all bound together by the incredibly powerful, strong nuclear force. As far as our best experiments can tell us today, particles like quarks and electrons seem to be true point particles. They appear to have no size at all, no internal parts, but that doesn't mean they're truly points. And this brings us to the edge of what's possible. As scientists pushed to probe smaller and smaller distances, they ran into a profound problem, one that has nothing to do with technology. To see a smaller object, you need to hit it with a higher energy particle. Think of it like this: to find out what's inside a box, you can shake it, or you can throw something at it. To see smaller details, you have to throw something harder. So, as you use more and more energy to try and see a smaller and smaller distance, this isn't a problem we can solve with better machines. It's a fundamental limit built into the fabric of reality. A distance below which the concept of measurement breaks down. A distance below which space itself might not be the smooth, continuous thing we imagine it to be. It might be grainy, or foamy, or something else our minds can't even picture. And that distance, that absolute final stop on our journey inward, is the Planck length. In the next part, we'll dive into exactly why this length exists, how physicists calculate this incredible number, and what it truly means when we say that trying to go smaller leads to contradictions that modern physics simply cannot resolve. It's a mind-bending trip, so stick around. Thanks for watching, and if you're enjoying this journey to the limits of reality, make sure to like and subscribe for more. As scientists pushed to see smaller and smaller, they hit a wall. But it wasn't a problem with their tools. It was a problem with reality itself. At a certain point, the universe simply refuses to be looked at any closer. To get why, we need to talk about energy. In our daily lives, looking at something feels passive. You just open your eyes, and information flows in. But on the tiny scales of quantum physics, measurement is an active, even violent, process. To see something microscopic, you have to poke it with something, and that poke always involves energy. Whether you use light or electrons, any probe you use has to interact with the particle you're observing, and that very interaction changes the particle. This is where things get weird. In the quantum world, particles aren't like tiny billiard balls with exact positions. They're more like fuzzy clouds of probability. Werner Heisenberg captured this strangeness in the 1920s with his famous uncertainty principle. It says there's a fundamental trade-off. You can't know certain pairs of a particle's properties with perfect accuracy at the same time. The most famous pair is position and momentum. The more precisely you try to pin down a particle's location, the more uncertain its momentum becomes, and vice versa. To measure a particle's position with pinpoint accuracy, you need a probe with a very short wavelength. But here's the catch. In physics, short wavelengths mean high energy. So, when your high-energy probe hits the particle to measure its position, it gives it a massive kick, sending its momentum haywire. There's no way around it. You cannot measure without disturbing. As you try to probe smaller and smaller distances, the energy required skyrockets, and eventually something even more dramatic happens. Remember Einstein's famous equation, E equals mc squared. It tells us that energy and mass are two sides of the same coin. If you concentrate enough energy into a tiny space, that energy starts to act like mass. And what does mass do? According to general relativity, it warps spacetime. So, when you blast an area with extreme energy to see what's happening at an incredibly small scale, you're not just a passive observer. You are actively reshaping the fabric of space itself. If you cram enough energy into a small enough region, the curvature of spacetime becomes so extreme that it collapses, forming a black hole. Think about that. Your very act of measurement creates a black hole that swallows up the very thing you were trying to see. The region you wanted to observe is now hidden forever behind an event horizon. Instead of revealing more detail, your measurement has completely erased it. This leads to a mind-blowing conclusion. There's a fundamental limit, a scale at which trying to measure a distance creates a black hole that is bigger than the distance you retrying to measure. Below this scale, observation becomes impossible, not just practically, but in principle. This ultimate limit is known as the Planck length. The Planck length isn't just some random number. It pops up naturally when you combine three of the most fundamental constants of nature. These numbers are like the universe's source code. They define the structure of our reality. First, you have the speed of light. It's not just how fast photons travel. It's the cosmic speed limit. It's the constant that stitches space and time together into a single fabric. Second is Planck's constant. This little number is the heart of quantum mechanics. It determines the size of quantum effects. It's the reason energy comes in discrete packets, or quanta, and why the subatomic world is so fuzzy and probabilistic. And third is the gravitational constant. This tells us the intrinsic strength of gravity. On our scale, gravity seems weak, but it dominates the cosmos because it's always attractive and adds up over vast distances. Now, if you take these three fundamental constants, the speed of light, Planck's constant, and the gravitational constant, and combine them in the only way that gives you a unit of length, you get the Planck length. That number is so small, it's almost impossible to comprehend. To give you some perspective, the Planck length is about 20 orders of magnitude smaller than a single proton. And a proton is already fantastically tiny. Let's try another analogy. Imagine you could take the Planck length and scale it up to the size of a single grain of sand. On that same scale, a single proton would be as large as the entire observable universe. This isn't just a poetic metaphor. It's the actual mathematical ratio between these scales. The gap between our world and the Planck scale is so immense that our intuition completely breaks down. At the Planck length, the two great pillars of modern physics, quantum mechanics and general relativity, collide. On one hand, you have the weird, probabilistic rules of the quantum world. On the other, you have the smooth, continuous spacetime of gravity. Our current theories were never designed to work together in this extreme realm. When you try to apply both at once, at these insane energies and tiny distances, the math just stops making sense. What happens to spacetime itself? The concepts of distance and time start to lose their meaning. The very geometry of space might begin to fluctuate violently. Some physicists call this idea spacetime foam. Instead of a smooth, flat sheet, spacetime at the Planck scale might be a churning, turbulent froth of quantum energy. Tiny virtual black holes could be constantly popping into existence and vanishing in an instant. Microscopic wormholes might briefly connect different points in space before disappearing. This isn't science fiction. It's the logical conclusion of pushing our best understood theories to their absolute limits. We don't know for sure if this picture is right, because we don't yet have a complete theory of quantum gravity to describe it. But what we do know is that the Planck length represents a fundamental boundary to our knowledge. It's the edge of the map, a frontier beyond which our current laws of physics fail us. So, what lies beyond this frontier? Is space continuous, or is it made of discrete, indivisible pixels? like a digital image? Is the universe fundamentally smooth or grainy? Next time, we'll dive into the leading theories that try to answer these questions and explore what physicists think spacetime itself is truly made of at its most fundamental level. Thanks for watching. If you enjoyed this journey to the edge of reality, make sure to like and subscribe for more deep dives into the mysteries of the cosmos. See you in the next one. Once we accept that there's a smallest meaningful length, a much deeper question naturally follows. What is space itself actually made of? Is it a smooth, continuous fabric that can be divided forever? Or does it come in discrete pieces, like pixels on a screen? For most of scientific history, space was assumed to be continuous. Between any 2 points, you could always find infinitely many other points. You could always divide a distance again and again, forever. This idea is deeply embedded in the math we use for physics, especially calculus. And in our everyday lives, this assumption works perfectly. You can walk halfway across a room, then halfway again, and so on, without ever hitting a smallest possible step. Motion feels smooth. Space feels completely uninterrupted. But quantum physics has repeatedly shown us that things we thought were continuous are actually not. Energy comes in discrete packets called quanta. Light comes in particles called photons. Atoms have fixed, distinct energy levels. Matter itself is quantized. This raises a fascinating possibility. What if space itself is also quantized? If space is quantized, then the Planck length would be the smallest possible unit of distance. Below this incredibly tiny scale, the very concept of distance would break down. Asking what's at half a Planck length would be like asking for half an atom in chemistry. The question just wouldn't make sense. Some theories of quantum gravity suggest exactly this. In these models, space isn't just a smooth background where things happen. Instead, space is something that exists because of deeper, underlying quantum structures. The idea of distance emerges from how these fundamental structures are arranged and connected to each other. A good way to picture this is to think about a digital image on your screen. From a distance, the picture looks smooth and continuous. Colors blend seamlessly, and shapes look solid. But if you zoom in far enough, you start to see the individual pixels. The smoothness was just an illusion created by the limits of your resolution. Space might work the same way. At the large scales we experience, it appears perfectly smooth and continuous, just as Einstein's equations describe it. But at the ridiculously tiny Planck scale, space might actually be made of discrete elements. Now, it's important to understand that these elements are unlike tiny cubes or bricks sitting asterisk inside asterisk of space. They asterisk are asterisk space. This is a crucial distinction. If space were made of tiny cubes arranged in a regular grid, that grid would create preferred directions. Physics would act differently if you moved along the grid's axis versus diagonally. But countless experiments have shown us that space has no preferred directions. The laws of physics are the same no matter which way you turn. So, if space is discrete, its structure must be more complex, something irregular, flexible, and relational, not fixed and rigid. Some theories describe space as a kind of network of connections. Distances arise from the relationships between the nodes in this network. Where the connections are strong and numerous, the distance is short. Where the connections are weak and sparse, the distance is long. In this view, space isn't a container that objects move through. Space is something that forms because of how these fundamental elements interact with each other. This idea radically changes how we think about something as basic as motion. If space is discrete, how does anything actually move? In classical physics, an object moves smoothly from one position to the next, passing through every single point in between. But if there are no points between two adjacent Planck units, there's no in-between to pass through. Motion at the deepest level might not be continuous at all. It might be a sequence of quantum jumps or transitions between discrete states of position. At our large human scale, these tiny, rapid transitions would blur together and appear as smooth, continuous motion, just like a movie appears smooth, even though it's made of thousands of individual static frames. This would mean that the smooth motion we see everywhere is an emergent phenomenon, not a fundamental property of reality, and it might not stop with space. Time could behave the same way. If there's a smallest possible length, there might also be a smallest possible unit of time called the Planck time. This is the time it takes for light to travel one Planck length. Below this unimaginably short interval, the concepts of before and after might lose their meaning. Time, just like space, could be quantized. If that's true, then the universe doesn't flow continuously like a river. It updates. Reality progresses in a series of incredibly rapid, discrete steps. Of course, those steps are so small and so fast that continuous time emerges naturally at human scales. This idea definitely challenges our intuition, but our intuition has failed us before when we've delved into the quantum realm. There's an even deeper implication here. If both space and time are quantized, then spacetime itself becomes a quantum object. That means it can exist in superpositions. It can fluctuate. The geometry of the universe is no longer fixed and absolute. At the Planck scale, distances might not have single, definite values. They could exist as a cloud of probabilities. Space itself could be fundamentally uncertain. And this isn't just about our inability to measure things precisely. It's about reality itself, lacking definite values until certain conditions are met. In a universe like that, the idea of a fixed background, a stage on which the drama of physics plays out, completely dissolves. The stage itself becomes part of the play. This brings us face to face with the limits of our own language. Our everyday concepts of space, distance, and motion all evolved in a world that is vastly different from the Planck scale. There's really no reason to expect these familiar ideas to apply unchanged at the deepest level of reality. Right now, physicists don't know for sure whether space is truly discrete or continuous. Different theories point to different answers. Some suggest that space is fundamentally granular. Others propose that it remains continuous, but we can't probe below the Planck length because of fundamental physical limits. But both sides agree on one thing. The Planck length marks a profound boundary, a point where our familiar descriptions of the world simply stop working. So, what happens when we apply these quantum fluctuations directly to spacetime itself? Why do many physicists believe the Planck scale is not a quiet, orderly place, but a violent, restless, and chaotic realm? But when we combine our two best theories of reality quantum mechanics and general relativity, something extraordinary happens. It all starts with the quantum vacuum. Quantum mechanics tells us that even the emptiest space is never truly empty. So, we know the quantum vacuum is alive. Here's where gravity comes in. Einstein's theory of general relativity tells us that any form of energy any at L curves spacetime. This includes the fleeting energy of those quantum fluctuations. Under normal, everyday conditions, these fluctuations are minuscule, and their gravitational pull is completely negligible. We'd never notice it. But everything changes as we zoom in, way in, down to the smallest possible scale, known as the Planck scale. This is a realm of incredibly small distances and unbelievably short moments in time. Here, the famous uncertainty principle of quantum mechanics takes over in a dramatic way. It allows for enormous fluctuations in energy. The smaller the region of space you look at, the larger the possible energy fluctuation can be. At the Planck scale, these energy fluctuations become so intense, so powerful, that their gravitational effects can no longer be ignored. Spacetime itself begins to heave and churn. Instead of being smooth and orderly, the very geometry of reality becomes turbulent. The legendary physicist John Wheeler gave this bizarre state of reality a fantastic name, spacetime foam, and the name is perfect. Imagine you're flying high above the ocean. From your vantage point, the surface looks smooth and flat. But as you get closer, you start to see waves. Closer still, you see whitecaps and spray. And if you could zoom in to the microscopic level, you'd see a chaotic mess of bubbles, spray, and turbulence. Wheeler suggested that spacetime behaves in exactly the same way. two regions of the universe might become temporarily linked, then disconnected again. It's a bit like temperature. You can't talk about the temperature of a single molecule. Temperature is an emergent property that arises from the collective motion of many, many molecules. At the smallest scales, temperature doesn't exist. At large scales, it becomes a meaningful concept. Perhaps space-time geometry is the same. At the deepest level, there is no smooth geometry, only a sea of quantum states. The smooth space and time we know and love only emerge when enough of these quantum states combine. This completely changes how we think about reality. Space and time are not the fundamental containers of the universe. They are emergent phenomena, arising from something deeper and more fundamental that we don't yet understand. This is precisely why our current theories break down at the Planck scale. General relativity assumes a smooth, continuous geometry. Quantum mechanics assumes a fixed, static background. Neither of these assumptions holds true when geometry itself becomes a quantum phenomenon. To go further, physics needs a new framework, a new theory. A theory where spacetime isn't just assumed, but is derived from more basic principles. A theory that finally unifies quantum mechanics and gravity into a single, coherent structure. This is the grand quest for a theory of quantum gravity. In our next video, we'll explore the first major attempt to build such a theory, one that replaces point-like particles with something even more fundamental, and suggests that the smallest building blocks of reality might be tiny, vibrating strings. Thanks for watching, and if you enjoyed this journey to the edge of reality, make sure to like, subscribe, and hit that bell so you don't miss our next adventure into the unknown. See you next time. Have you ever wondered what the universe is truly made of? We're taught that everything is built from tiny particles, like electrons and quarks. But what if that's not the whole story? What if, at the deepest level of reality, everything is made of something else entirely? When physicists started exploring the very fabric of spacetime, they ran into a problem. At the smallest, most fundamental scales, spacetime itself might be a wildly fluctuating, chaotic sea. In a world like that, the idea of a simple point-like particle just doesn't hold up. If the stage itself is unstable, how can the actors on it be simple points? This puzzle forced us to look for something more fundamental, a hidden layer beneath everything we see and know. One of the most audacious and mind-bending ideas to emerge from this search is called string theory. It starts with a simple, yet revolutionary claim. The fundamental building blocks of our universe are not points. They are tiny, one-dimensional, vibrating strands of energy called strings. To us, they look like points because we can't possibly see their true form. But at their core, they have length and they can vibrate. Think of a guitar string. By plucking it in different ways, you can produce a whole range of different musical notes. String theory proposes that the universe works in a similar way. The fundamental strings can vibrate in different patterns, and each unique vibration corresponds to a different particle. One pattern of vibration gives us an electron, another gives us a quark. Suddenly, the entire zoo of particles in the universe isn't a random collection of separate things. They are all just different notes played on the same fundamental string. Instead of dozens of unrelated particles, there's just one basic object, vibrating in different ways. But here's where it gets truly amazing. When physicists explored the mathematics of these vibrating strings, they found something they weren't even looking for. One of the vibrational modes of the string perfectly matched the properties of a hypothetical particle called the graviton. The graviton is the quantum particle thought to carry the force of gravity. This means that in string theory, gravity isn't something you have to add in manually. It just emerges naturally from the theory itself. String theory was originally developed in the 1960s to describe the strong nuclear force that holds atomic nuclei together. Not gravity. But gravity just appeared, a hidden gift within the mathematics. This unexpected discovery immediately propelled string theory to the forefront as a leading candidate for a theory of everything, a unified theory of quantum mechanics and gravity. However, this beautiful theory comes with a very strange requirement. The math behind string theory simply does not work in the 3 dimensions of space that we experience every day. For the equations to be consistent, the universe must have extraspatial dimensions. So, the obvious question is, where are they? If these extra dimensions exist, why can't we see them or move through them? String theory has a fascinating answer. They are compactified. Imagine they are curled up into tiny, intricate shapes, so small that they are completely invisible to us and our most sensitive instruments. A good analogy is a garden hose. From far away, it looks like a simple, one-dimensional line. You can only move back and forth along its length. But if you get very close, like an ant crawling on its surface, you discover a second dimension, the circular path around the hose's circumference. The ant can move along the length and around the circle, experiencing both dimensions. From our distant macroscopic viewpoint, that second dimension is hidden. String theory suggests that spacetime itself is like this. At every single point in our familiar 3-dimensional space, there are 6 or 7 additional dimensions curled up into a tiny, complex geometric shape, possibly as small as the Planck length. These shapes aren't just random squiggles. They are precise, intricate structures called Calabi-Yau manifolds. And here, the crucial part, the exact shape of these extra dimensions determines the laws of physics in our universe. The geometry of these hidden dimensions dictates the properties of the strings vibrating within them. It sets the mass of an electron, the strength of the electromagnetic force, and the entire menu of particles that can exist. In a sense, the physics we observe is a reflection of a hidden geometry. change the shape of those tiny, curled-up dimensions, and you would get a completely different universe with different particles and different forces. This is both incredibly exciting and deeply unsettling. It means the fundamental laws of nature might not be so fundamental after all. They could be byproducts of geometry at an unimaginably small scale. But this leads to a massive problem. It turns out there isn't just one possible shape for these extra dimensions. The mathematics allows for an astronomical number of possibilities. We're talking about maybe 10 to the power of 500 different shapes, a number so vast it's greater than the number of atoms in the known universe. Each of these possible shapes corresponds to a different possible universe with its own set of physical laws. This vast collection of possibilities is known as the string theory landscape. But if there are so many options, why does our universe have the specific laws that it does? Why this particular geometry and not any of the countless others? One controversial idea is the multiverse. Perhaps all of these configurations exist as separate universes, and we just happen to live in one of the rare ones where the laws of physics allow for the formation of galaxies, stars, planets, and ultimately, life. This is called the anthropic principle. It suggests we see the laws we do because if they were any different, we wouldn't be here to observe them. For many physicists, this is an unsatisfying explanation, as it steps away from the goal of uniquely predicting the universe's properties from first principles. And that brings us to the biggest challenge facing string theory today. Despite its mathematical elegance and profound ideas, it has yet to make a single clear, testable prediction that could be verified with current technology. Its predictions, like the existence of strings and extra dimensions, are all tied to the Planck scale, an energy level far beyond the reach of any particle accelerator we can build. But science demands evidence, and string theory's lack of testable predictions has led some physicists to explore other paths. String theory is not the only game in town when it comes to uniting gravity and quantum mechanics. Another major approach, called loop quantum gravity, takes a radically different starting point. Instead of replacing particles with strings, it attempts to quantize space and time themselves, building them from the ground up out of discrete, indivisible units. So, what if space isn't a smooth, continuous background, but a network of interconnected loops? What if area and volume themselves come in tiny, fundamental packets? In our next video, we'll dive into the world of loop quantum gravity and explore this fascinating alternative vision of reality. Thanks for watching. If you enjoyed this journey to the edge of physics, don't forget to like, subscribe, and hit the bell so you don't miss our next adventure. See you then. We often talk about string theory, where tiny strings vibrate in a pre-existing space. But there's another, mind-bending idea out there. What if space itself isn't fundamental at all? What if it emerges from something deeper, from a network of pure relationships? This is the core concept behind a theory called loop quantum gravity. Unlike string theory, which tries to unify all of nature's forces in one go, loop quantum gravity has a laser focus on just one problem: how to make gravity work with the rules of quantum mechanics. It starts with Einstein's theory of general relativity, but it rewrites it in a new language, a language that can be Instead, it's made of discrete, indivisible units. But don't picture these as tiny cubes floating in an empty void. These units are the very fabric of space. The fundamental building blocks are called loops, and these loops connect to form vast networks, sometimes called spin networks. Think of it like this: each loop is a quantum of the gravitational field. Distance, area, volume, all of it emerges from the pattern of connections. In this picture, there's a smallest possible area and a smallest possible volume, both tied directly to the incredibly tiny Planck length. Space becomes granular. That's how space works in loop quantum gravity. The smooth spacetime of Einstein's relativity is what we perceive at large scales. An average effect of countless quantum threads weaving together. This perspective has some really deep implications. Since the loops don't exist inside space, but actually are space, there's no fixed background. Geometry isn't a static stage. It's a dynamic, evolving character in the cosmic drama. Connections can form, dissolve, and rearrange themselves. It just transitions into a new quantum phase. This is still speculative, but it's a mathematically consistent possibility within the theory. This same logic can be applied to the entire universe. When we run the clock backwards, classical physics predicts the Big Bang was a singularity, infinitely hot, infinitely dense point where everything began. Loop quantum cosmology, the application of these ideas to the whole universe, suggests something different. As the early universe contracted to an unimaginable density, quantum geometry effects would have taken over. instead of collapsing into a singular point, the universe would have reached a minimum size and then bounced. The Big Bang might not have been a beginning at all, but a transition from a previous, contracting cosmic phase. Time didn't start at the Big Bang. It flowed right through it. This big bounce could potentially explain some of the biggest puzzles in cosmology, like why the universe is so remarkably smooth on large scales. Of course, like any frontier theory, loop quantum gravity has its challenges. But its conceptual power is undeniable. It shows us a path where space and time are not fundamental but are emergent quantum phenomena. It paints a picture of a granular, woven geometry that resolves the paradox of singularities. Ultimately, both string theory and loop quantum gravity point to the same profound conclusion. At the Planck scale, our everyday reality dissolves. This leads us to an even deeper question. If space and time are not the ultimate foundation of reality, then what is? Join me in the next video, where we'll explore the radical idea that information itself might be the bedrock of existence, blurring the line between physics and pure data. After scientists started toying with theories where space itself is built from tiny quantum bits, they began to ask an even deeper question. If space and time aren't fundamental, then what is? What could possibly lie beneath geometry itself? Surprisingly, a lot of modern ideas point not to something physical, but to something abstract: information. Now, in the physics we learned in school, information is just something we use to describe a system. It's not what the system is actually made of. But quantum physics really messes with this idea. In the quantum world, information is physical. You can't just copy it whenever you want. You definitely can't destroy it. It plays by very strict rules. This shift in thinking has led physicists to suspect that information might be the true bedrock of reality, even more fundamental than particles or space. One of the biggest clues for this comes from black holes. Black holes are like cosmic criminals. They seem to destroy information. When something falls into a black hole, all the little details about it seem to vanish forever behind the event horizon. All we can see from the outside is its mass, charge, and spin. Everything else appears to be lost. But here's the problem. Quantum mechanics absolutely forbids information loss. If information really does disappear inside a black hole, then our entire theory of quantum mechanics breaks down. This puzzle is famously known as the black hole information paradox. For decades, physicists have been in a heated debate. Is information truly destroyed by black holes? Or is it somehow saved? The answer that's slowly coming into focus suggests that information is never lost. It's actually encoded in very subtle ways, in the correlations between particles. This leads to a truly mind-blowing conclusion. The geometry of space around a black hole might be directly tied to the information stored on its boundary. This idea is formalized in what's called the holographic principle. The holographic principle suggests that all the information contained inside a volume of space can be fully described by what's happening on its outer boundary. Think of a hologram on a credit card. It's a two-dimensional surface that encodes a full three-dimensional image. The holographic principle proposes that our entire universe might work the same way, encoding its information on some lower dimensional boundary. In this view, space isn't the fundamental stage. It's an emergent property, a projection of information. Once physicists started thinking this way, they had a powerful new realization. If information creates geometry, then maybe distance itself is just a measure of how information is shared. Imagine two regions of space. If they are strongly connected and share a lot of information, they are close together. If they are weakly connected, they are far apart. Distance becomes an expression of how entangled things are. Quantum entanglement is that spooky phenomenon where particles share information no matter how far apart they are. If you measure one entangled particle, its partner instantly knows and responds, even if it's across the galaxy. Now, entanglement doesn't let you send signals faster than light, but it does reveal a deep, hidden connection in the fabric of reality. And here's where it gets really wild. Physicists began to notice that when you have quantum systems entangled in specific patterns, the math that describes their entanglement looks exactly like the math that describes curved spacetime. In some theoretical models, if you increase the entanglement between different regions, the space between them becomes smoother and more connected. But if you reduce that entanglement, space can actually tear apart. This strongly suggests that the geometry of spacetime might be built directly from the web of quantum entanglement. So, in this picture, space isn't a container that holds information. Space is the pattern created by the relationships between bits of information. This isn't just a metaphor. It's a precise mathematical connection called holographic duality. In these models, a quantum system that doesn't have gravity can be mathematically identical to a universe with gravity in a higher dimension. Gravity literally emerges from quantum information. Calculations you do in the simple quantum system can perfectly reproduce black holes, curved spacetime, and the dynamics of gravity. What looks like gravity in one description is just the flow of information in another. This is one of the most profound insights in modern physics. It suggests spacetime is not fundamental. It's an emergent property arising from countless quantum bits interacting according to the rules of information. If you could zoom in all the way to the Planck scale, the smallest possible scale in the universe, geometry would dissolve. What you'd find instead are quantum states and the web of entanglement connecting them. This perspective also helps explain why spacetime might be discrete, made of tiny, indivisible units. Information itself comes in finite units, or bits. A quantum system can only hold a finite amount of information. So, if space is built from information, it can't be infinitely divisible. The famous Planck length might represent the smallest meaningful unit of geometric information. Below that scale, talking about distance just doesn't make sense anymore. There are no more bits of information to define what space even is. This changes how we think about everything, even motion. In this fundamental description, objects don't really move through space. Instead, the patterns of entanglement that define the object simply evolve. What we perceive as an object moving from point A to point B is actually the information that defines it becoming correlated with different regions of this vast information network. This view completely dissolves the old distinction between matter and space. Particles aren't little things living inside space. Particles and space are two different aspects of the same underlying information network. Matter and geometry are just two sides of the same coin. This is deeply counterintuitive, I know. But physics has shown us time and time again that our everyday intuition completely fails at the most fundamental scales. Electricity and magnetism once seemed totally separate. Space and time once seemed absolute and distinct. Mass and energy seemed like different things. Each time, a deeper understanding revealed a hidden unity. The idea that information is the foundation of spacetime could be the next great unification in that long tradition. However, it's important to remember that this idea is still a work in progress. We don't have a complete theory showing exactly how our specific universe emerges from information. We have fascinating toy models, we have partial results, and we have very deep hints. But the direction of travel is clear. The Planck scale isn't just where space gets really, really small. It's where space stops being the main character. Below that scale, reality may not be defined by geometry, but by information. In our next video, we're going to travel back to the very beginning of time. We'll explore how this Planck scale physics may have shaped the birth of the cosmos itself, and why the very largest structures in the universe might carry the ancient imprint of the smallest possible scale. Thanks for watching, and don't forget to subscribe for more journeys to the edge of reality. Have you ever wondered how the vast, sprawling universe we see, with its billions of galaxies, came to be? What if I told you the answer lies not in the stars, but in a scale so infinitesimally small it defies imagination? What if the entire cosmos was shaped by the very smallest thing possible? It all starts with an idea that might blow your mind. Space and time, the very fabric of our reality, might not be fundamental. Instead, they could be emerging from something deeper, something called quantum geometry. If this is true, then the birth of our universe isn't just a story from the distant past. It's a cosmic laboratory, the only place we can see the effects of this ultra-small scale. Let's rewind the clock. When we look out at the night sky, we see an expanding universe. Galaxies are flying away from us, and the farther they are, the faster they go. This means that in the past, everything was much closer, hotter, and denser. If we follow this logic all the way back using our current understanding of physics, we hit a Walla singularity, a point of infinite density and temperature where everything we know breaks down. But here's the thing about singularities: they're not real. They're a sign that our theory, Einstein's general relativity, has reached its limit. We need something more fundamental, a theory of quantum gravity. This brings us to the Planck epoch, the very first sliver of a moment after the universe began. We're talking about 1 Planck time, a unit of time so short it makes a second feel like an eternity. During this epoch, the entire observable universe was crammed into a space smaller than a single proton, at temperatures hotter than anything we can comprehend. In this extreme environment, our familiar concepts of space and time likely didn't exist. Instead of a smooth, continuous reality, the universe might have been a fuzzy, chaotic quantum state. Think about that. Concepts like before and after might not have even had meaning. Time itself might be an emergent property, something that only appeared once the universe cooled and organized itself into a stable structure. It's like how temperature only makes sense when you have a lot of particles. Maybe time only makes sense once the quantum fuzziness settled down. Is it possible to test physics at a scale we can never, ever reach directly? The answer is a bit tricky. We can't just build a machine powerful enough to see the Planck length. The energy needed would be more than anything humanity could ever hope to create. To give you an idea, a particle accelerator that could reach Planck energies would have to be bigger than the entire observable universe. But here's the thing. Physics has never been just about direct access. Instead, scientists look for indirect clues, assigning effects, subtle differences, small fingerprints left behind by these fundamental processes. One of the most exciting ideas is that spacetime isn't smooth and continuous, but discrete, like pixels on a screen. If spacetime has a granular or chunky structure at the Planck scale, then particles traveling through it might experience tiny disturbances. These would be unimaginably small, but over enormous distances, they could add up to something we could actually measure. And what travels enormous distances? Light. Light is the perfect messenger for this. Some photons have been traveling for billions of years before finally reaching us here on Earth. If space-time affects their journey even slightly, those effects might reveal themselves after such a long time. Some quantum gravity models predict that very high-energy photons might travel at a slightly different speed than lower-energy photons. This is where gamma-ray bursts come in. Gamma-ray bursts are some of the most energetic events we know of in the universe. They unleash a colossal amount of energy in a very short time, producing photons across a huge range of energies. Crucially, these photons are all released at almost exactly the same moment. So, if high-energy photons traveled at a different speed than low-energy ones, they would arrive at Earth at different times. Astronomers have been carefully studying countless gamma-ray bursts, measuring the arrival times of their photons with incredible precision. And so far, nothing. No consistent energy-dependent delays have been seen. But this absence of evidence is actually powerful. It tells us that if spacetime is discrete, its effects must be extremely subtle. Many proposed theories of quantum gravity have already been ruled out simply by these observations. Another approach involves gravitational waves. These are ripples in spacetime itself, created by massive, accelerating objects like merging black holes and neutron stars. Unlike light, gravitational waves barely interact with matter. They carry information directly from the source, giving us a clean look at the geometry of spacetime. If quantum gravity modifies spacetime at the smallest scales, it might slightly change how these waves travel. Again, so far, every gravitational wave we've detected behaves exactly as predicted by Einstein's classical theory of general relativity. Their speeds, their shapes, and how they lose energy all match his equations with remarkable precision. This puts very strong limits on what any new theory of quantum gravity can look like. But the story is far from over. Future detectors will be much more sensitive. We're planning space-based observatories that will be able to detect lower frequency waves, perhaps from supermassive black holes merging, or even from primordial gravitational waves from the early universe itself. Primordial gravitational waves would be the ultimate prize. These waves would have been generated during inflation, a period right after the Big Bang, when tiny quantum fluctuations in space-time itself were stretched to cosmic scales. Detecting them would be like finding a fossil from the moment of creation, giving us direct information about physics operating at energies close to the Planck scale. Then there's the world of particle physics. Even if quantum gravity effects are tiny at the energies we can reach in our accelerators, they might still produce tiny corrections to processes we already know about. Modern experiments measure particle properties with mind-boggling accuracy. Sometimes they can detect deviations as small as 1 part in a trillion. So far, no definitive signs of quantum gravity have shown up. But each time an experiment comes back with a null result, it helps us narrow down the range of possible theories. It's like we're crossing off incorrect answers on a massive, cosmic multiple-choice test. Cosmology, the study of the universe as a whole, also offers clues. The large-scale structure of the universe, the way galaxies and empty voids are distributed, is a reflection of the physics of the early universe. By mapping this structure with ever-increasing precision, scientists can test different models of inflation and quantum fluctuations. Some of these models predict subtle statistical patterns that could hint at Planck scale effects. Others predict slight deviations from the perfect randomness we'd otherwise expect. These patterns are incredibly difficult to spot, but massive surveys are underway right now, scanning the skies to create the most detailed maps of the cosmos ever made. There are also tabletop experiments pushing the very limits of quantum mechanics itself. Some researchers are exploring whether gravity can exist in a quantum superposition. Imagine you could place 2 tiny masses into a quantum state where each one is in 2 places at once. If they then become entangled purely through their gravitational interaction, it would be a landmark discovery. It would prove that gravity is fundamentally a quantum force. These experiments don't reach the Planck scale, of course, but they test whether gravity plays by quantum rules, which is a critical piece of the puzzle. Atomic clocks are another amazing tool. Modern atomic clocks are so precise that they can detect the difference in the flow of time caused by gravity over a height change of just a few centimeters. It sounds like science fiction, but it's real. Some speculative models of quantum gravity predict tiny deviations from general relativity that just might, show up in these ultra-precise timing experiments. Again, no anomalies have been confirmed yet, but the precision of these clocks keeps improving year after year. So what's the big picture here? A clear pattern emerges. The Planck scale isn't unreachable because it's irrelevant. It's unreachable because it is so fundamental. Its effects are subtle, indirect, and deeply woven into the fabric of reality itself. We aren't searching for some dramatic breakdown of physics where everything we know is suddenly wrong. We're searching for whispers. Every experiment that finds nothing rules out entire families of theories. In our next video, we'll take a step back and think about what the Planck length really represents philosophically, not just as a number in an equation, but as a boundary of our knowledge, and what it tells us about the limits of human understanding. Thanks for watching, and I hope you'll join me for that. Don't forget to like and subscribe for more. As our quest for experimental evidence continues, many physicists now see the Planck length in a new light. It's not just some incredibly small number. It may represent a fundamental boundary to what we can ever know. Throughout history, science has repeatedly bumped into limits. Not limits of our curiosity, but limits imposed by nature itself. The speed of light is one such famous limit. Absolute zero temperature is another. And the Planck length might just belong in this exclusive club. It marks a point where our most basic questions stop making sense. Think about it. Below the Planck length, asking where something is might no longer be a meaningful question. Asking when something happens could be just as pointless. The very concepts of position and time, which feel so fundamental to our experience, might simply dissolve. They may not exist in the way we imagine them to. This idea challenges a very deep assumption that has guided physics for centuries: reductionism. The idea that if you want to understand something, you just break it down into its smaller and smaller parts. We broke molecules into atoms, atoms into nuclei, and electrons, nuclei into quarks. And each step revealed a deeper, more fundamental structure. But the Planck length suggests this process might have an end. There may be no smaller pieces to analyze. Instead of finding smaller objects, we find the limits of our very language of description. This doesn't mean reality stops existing below the Planck scale. It means our way of talking about it stops working. The universe might still be there, but not in terms of distance, time, or objects. It might exist as something far more abstract, like pure quantum states, or patterns of information without any geometry at all. This forces us to rethink what it even means to understand something. We often assume that to understand, we must be able to picture it in our minds. But modern physics has repeatedly shown us that reality doesn't owe us that kind of visual intuition. Let's be honest, no one truly visualizes quantum superposition or the elegant curve of spacetime. We accept them because the math works and the experiments confirm the predictions. The Planck scale might be the ultimate example of this. It could be real, indirectly measurable, and mathematically describable, but completely beyond our ability to visualize. This leads to a profound philosophical shift. Perhaps physics doesn't describe what reality asterisk is asterisk, but rather how reality asterisk behaves asterisk when we observe it under certain conditions. And below the Planck length, the very conditions required for observation might no longer exist. Measurement itself could become impossible. To measure a distance, you need a ruler. But at the Planck scale, any conceivable ruler would have so much energy packed into such a tiny space that it would instantly collapse into a black hole, destroying what you were trying to measure. To measure time, you need a clock. But at the Planck scale, time itself may not be a smooth, ticking progression. This suggests the Planck length isn't just small, it's inaccessible by principle. Now, this doesn't mean physics has failed. It means the role of physics might be changing. Instead of describing what happens at every single scale, physics might be in the business of describing how descriptions themselves emerge from a more fundamental reality. Space, time, and even causality could be what we call effective concepts, useful descriptions that work perfectly well in our world, but aren't fundamental building blocks of the universe. This idea aligns beautifully with a growing trend in theoretical physics, the notion that the deepest level of reality is not geometric, but relational. That reality is ultimately made of relationships, not things. In a framework like that, asking for the smallest distance is like asking for the smallest relationship. There might be a minimum, meaningful relation, a point beyond which all distinctions simply dissolve into a unified whole. This perspective also reshapes the role of mathematics. The Planck length isn't some random number we pulled out of a hat. It emerges from a simple dimensional analysis. It's the one and only length you can construct using the three fundamental constants of nature: the speed of light, Planck's constant, and the gravitational constant. This powerful fact suggests it's not arbitrary. It's built into the very structure of physical law. It's as if the universe is telling us, this is the resolution limit. You can think of it like a digital image. An image has a pixel size, and beyond that size, you can't resolve any more detail. Reality itself might have a fundamental resolution, and the Planck length is that pixel size. But there's a crucial difference. Unlike the pixels on your screen, which are laid out in a neat, static grid, these fundamental units of reality are dynamic. They fluctuate. They exist in a superposition of states. This means reality isn't grainy like a pile of sand. It's grainy like quantum probability. At the large scales we experience every day, this graininess averages out, and smooth space and flowing time emerge naturally. But at the tiniest scales, that graininess dominates everything. This raises another mind-bending question. If there's a smallest possible length, is there also a smallest possible amount of information? Is reality, at its core, fundamentally finite? Some physicists believe the answer is yes. They argue that the amount of information you can pack into any region of space is finite and, strangely, proportional to its surface area, not its volume. This is the holographic principle, an idea that once again points to information as the true foundation of everything. If information is finite, then the idea of infinite divisibility just can't be true. There must be a smallest meaningful unit. The Planck length could be the physical manifestation of that unit. This doesn't make the universe simpler. It makes it infinitely stranger and more wonderful. It suggests that beneath the smooth, continuous reality we perceive, there lies a finite, discrete, probabilistic structure. A structure that we can never directly access, only infer from the world it creates. And yet, from this bizarre quantum foam foundation, everything we know emerges: stars, galaxies, life, consciousness, your own thoughts. The calm, vast night sky you see above you is built from processes operating at scales so small that our imagination can't even begin to grasp them. So, where does this leave us? In the next part, we'll bring all these incredible ideas together and ask the final practical question: why does any of this matter? What does knowing about the Planck length change about how we see ourselves and our place in the cosmos? Thanks for watching, and I'll see you in the next video. We've journeyed from our familiar human world all the way down to the Planck length, the absolute smallest scale imaginable. And as we arrive here, it's clear this isn't just about physics anymore. This idea, this infinitesimally tiny limit, quietly reshapes how we think about existence itself. The smallest possible scale forces us to reconsider what it even means to be a part of the universe. It's trillions upon trillions of times smaller than an atom, far beyond anything we could ever hope to see or touch. And yet, everything you are, everything you experience, is built upon it. Every single particle, every force that holds things together, every fleeting moment of time, emerges from the fundamental processes happening right at this scale. This simple fact leads to a truly humbling realization. We often imagine ourselves as separate observers, living on a small, isolated planet adrift in a vast, empty cosmos. The very same quantum fabric that governs the smallest possible distances also weaves together the largest galaxies. The same fundamental rules shape the inside of an atom and the grand evolution of the entire universe. So, here is a thought that might change how you see yourself. You are not simply placed asterisk inside asterisk the universe. You are a pattern asterisk formed by asterisk it. Your body is a collection of atoms, which are made of particles, which are just excitations in quantum fields. Those fields only exist because spacetime itself allows them to. And spacetime, as we understand it, only has a definite structure because of what's happening at the Planck scale. Everything connects downward, tracing back to the very same foundation. You are, quite literally, woven from the fabric of spacetime. This perspective reveals that complexity is a natural, emergent property of the universe. The cosmos doesn't need a special set of instructions to create intricate structures. Given a few fundamental laws and an immense amount of time, simple rules blossom into astonishing richness. Galaxies coalesce from dust. Stars ignite under their own gravity. Chemistry emerges from the dance of atoms. Life appears on a rocky world. And eventually, consciousness develops. All of this incredible unfolding rests on the quiet, unwavering stability of the smallest scale. The Planck length also reframes how we think about limits. We tend to see limits as failures, as a sign that our knowledge has hit a wall. But in physics, limits often reveal a deeper, more profound order. The speed of light, for example, is a limit on motion, but it's what makes cause and effect possible. Absolute zero is a limit on how cold something can get, but it's the bedrock of thermodynamics. In the same way, the Planck length might be a limit on how precisely we can measure reality, but it's also what gives reality its fundamental resolution. It's like the pixel size of our universe. It tells us that not everything can be known in the way we might intuitively expect. And that's not a discouraging thought, it's a clarifying one. It reminds us that understanding the universe doesn't require dominating it. We don't need to control or access every single scale to appreciate its beauty. Think about it this way. At our human scale, the universe seems quiet and slow. Stars drift across the sky over hours, and cosmic changes take millions of years. But if you could zoom in to the Planck scale, you'd find a universe that is restless, chaotic, and alive with quantum uncertainty. Both of these descriptions are true. They are simply different views of the same reality, seen at different resolutions. This dual nature also affects how we perceive time. Your life unfolds over decades. Civilizations rise and fall over centuries. Stars live for billions of years. Yet, the fundamental ticking of reality's clock might be happening in intervals of time, so unimaginably small they make a nanosecond look like an eternity. The time you experience the steady rhythm of seconds, minutes, and hours is an emergent property, a slow melody built from countless microscopic, ultra-fast changes. You are a slow, thoughtful process, built from incredibly fast ones. There's something strangely comforting in this perspective. It places human existence not as some accident layered on top of a cold, indifferent universe, but deeply within its physical laws. Our thoughts, our awareness, our consciousness, these aren't bizarre flukes. They are natural outcomes of physical laws unfolding over immense scales of space and time. It shows us that beneath apparent simplicity lies an extraordinary structure. Beneath stillness, there is constant motion. Beneath our illusion of certainty, there is fundamental probability. And yet, despite all this underlying complexity and chaos, our universe is remarkably stable. The fundamental constants that govern reality have held true since the earliest moments after the Big Bang. The same structures persist. The same laws of physics apply everywhere we have ever looked. This stability is what allows for meaning. If the universe were chaotic at every scale, nothing could ever endure, nothing could form. But because there is a smallest scale, a stable foundation, larger structures can form and persist long enough to matter, long enough for us to be here, thinking about it. In this sense, the Planck length isn't just a physical limit, it's a foundation. It is the quiet, unspoken agreement that allows reality to exist at all. It's the ultimate source of the order that we see all around us. So far, we've been looking inward and downward into the very structure of what is, but now it's time to look forward. What does the future of physics hold? What new secrets might we uncover about this smallest of all scales? Will humanity one day understand what lies even deeper, perhaps beneath space and time itself? The quest for answers continues. Thanks for watching. As physics pushes forward, the Planck length stands as both a destination and a guide. It's not a place scientists expect to visit directly, but it silently shapes the very questions they ask and the paths they explore. The future of fundamental physics, in many ways, is a long conversation with this smallest of all scales. One path forward relies on observation, not construction. Humanity may never build an instrument that can probe Planck-length distances directly, but the universe itself provides a natural laboratory. Extreme environments already exist out there, places where energy, density, and the curvature of spacetime approach the absolute limits set by nature. Black holes are a perfect example. Near the event horizon, gravity becomes overwhelmingly powerful. Time slows to a crawl, space stretches like taffy, and quantum effects start to become significant. While these regions are still a long way from the Planck scale itself, they might hold subtle signatures of quantum gravity. As our gravitational wave observatories get more sensitive, scientists will listen more closely to black hole mergers. The final violent moments before two black holes combine are governed by extreme space-time curvature. Any tiny deviation from what classical physics predicts could be a hint of a deeper, more fundamental structure to reality. Another clue comes from the very beginning of the universe. The theory of cosmic inflation, if we can confirm it in greater detail, might offer the clearest indirect window into Planck scale physics. The idea is that tiny quantum fluctuations, born in the first moments of the universe, were stretched to cosmic size. These fluctuations may still carry the fingerprints of the fundamental rules that governed our universe at its birth. Future observations of the cosmic microwave background, S polarization, and the search for primordial gravitational waves could reveal information about energy scales incredibly close to the Planck regime. These signals won't give us all the answers, but they would dramatically narrow down the possibilities. Meanwhile, our theories are also evolving. Physicists are seriously exploring the radical idea that spacetime itself might not be fundamental. Instead of trying to quantize gravity, they're asking if gravity could emerge from something even deeper. Concepts from quantum information theory, thermodynamics, and computation are now becoming part of the foundations of physics. Some of these new approaches suggest that the geometry of spacetime actually arises from complex patterns of quantum entanglement. Others propose that gravity behaves more like an entropic force, emerging from constraints on information rather than a fundamental interaction. If these ideas are correct, the Planck length might not be a physical boundary in space, but a boundary in our description of it. It would mark the scale where the familiar language of geometry gives way to the language of information. This would mean asking what exists below the Planck length is like asking what exists below a single bit of information. The question itself loses its meaning because there's nothing smaller in the language of that theory. Quantum computing could also play a crucial role. As these incredible machines become more powerful, they might be able to simulate simplified models of quantum gravity. These simulations won't recreate our universe in a box, but they could reveal how space-time-like behavior emerges from purely quantum systems. We've already seen small quantum systems used to model aspects of holography and emergent geometry. As the technology advances, these simulations will only become more sophisticated and insightful. Then there's the frontier of precision measurement. Our atomic clocks, interferometers, and quantum sensors are constantly improving. Each new order of magnitude in precision allows us to test physics in ways we previously thought impossible. Even if Planck scale effects are incredibly suppressed, they might leave faint, almost imperceptible traces that our most sensitive instruments can one day detect. The history of physics teaches us that patience is often rewarded. Phenomena once thought forever unobservable, like gravitational waves, eventually became detectable through sheer persistence and ingenuity. The Planck scale might follow a similar path, revealing itself not through brute force, but through subtle inference and clever observation. A philosophical evolution is also underway. Physicists are becoming more comfortable with the idea that some questions may not have answers in the traditional sense. Asking what lies below the Planck length might be like asking what plus north of the North Pole. The question assumes a framework, a continuous, smooth map that simply no longer applies at that point. This doesn't diminish science, it refines it. Understanding the limits of our descriptions is, in itself, a profound form of understanding. The Planck length may be telling us that reality is finite in its information content, relational in its structure, and emergent in its geometry. It might be inviting us to abandon our long-held idea of a perfectly continuous universe, and instead embrace one that is fundamentally discrete, built from individual units, and governed by the laws of probability. If that's the case, the future of physics won't be about finding ever smaller pieces, but about understanding ever deeper patterns. In the end, the Planck length represents more than just a limit for physics. It's a monument to human curiosity. It's a testament to our drive to understand the universe from its grandest cosmic structures down to its most fundamental, indivisible nature. This smallest of all possible scales may just be one of the most meaningful ideas we've ever discovered, constantly pushing us toward a deeper, more elegant understanding of everything. Thanks for watching. As we approach the end of this journey, the Planck length begins to look less like a technical detail and more like a message written into the very structure of reality. It tells us that the universe is not infinitely divisible. It tells us that there is a point beyond which our familiar questions simply no longer apply. For most of history, we humans believed that if something couldn't be seen, it was just too small or too far away. We thought better tools would eventually reveal it. The Planck length challenges this belief head-on. It suggests that some limits aren't temporary, they are permanent, and that is a profound shift in thinking. The universe may not allow for infinite detail. There might be a maximum resolution built into existence itself. Think about it like this. A digital image has a fixed number of pixels. If you zoom in too far, you don't see more detail. You just see the pixels. Reality may have a similar, smallest unit of distinction. Now, this doesn't make the universe crude or simple. It makes it precise. Precision doesn't require infinity. It just requires consistency. And the Planck length represents the exact point where consistency demands restraint. Below this incredibly tiny scale, the concepts we rely on every single day just collapse. Distance loses its meaning. Time loses its order. Cause and effect might even blur into one. Reality doesn't disappear, but it starts speaking a language we don't understand. This is why any attempt to visualize the Planck scale always fails. Visualization assumes geometry, the world of shapes and spaces we know. But the Planck scale may exist before geometry even comes into being. This forces a truly humbling realization. Our human intuition evolved to navigate a world of meters and seconds, to throw a spear or catch a ball. It was never designed to understand reality at its deepest, most fundamental level. Yet, through the power of mathematics and observation, we can still reach beyond our intuition. This is one of humanity's quiet, unsung achievements. We can't imagine the Planck length, but we can understand its consequences. We can see how it stabilizes physics, how it resolves the troublesome infinities that pop up in our equations, and how it protects reality from contradicting itself. Without a smallest length, the quantum fluctuations that happen everywhere, all the time, would grow without any bound, tearing the fabric of space apart. Without limits, gravity would relentlessly collapse everything into singularities, points of infinite density. The Planck length acts as a cosmic regulator, a quiet rule that keeps the entire universe coherent and stable. In this sense, it's not an obstacle to our understanding. It's a safeguard. It ensures that reality remains describable, that it can be understood at all. This also reframes the whole idea of mystery. We often see a mystery as something just waiting to be solved, a puzzle with a missing piece. But some mysteries might be structural. They exist because of how reality is built, not because we're missing some crucial information. The Planck length might be exactly that kind of mystery. Not a puzzle to be completed, but a fundamental boundary to be respected. This doesn't mean that scientific progress just stops here. It means that progress changes direction. Instead of digging ever deeper into smaller and smaller scales, physics might need to turn sideways. It might need to seek connections, to look for patterns and emergent principles that arise from the whole system. Understanding how spacetime, matter, and information all arise together might become more important than probing ever smaller distances. In this light, the Planck length isn't the bottom of reality. It's the seam where different descriptions of reality meet: quantum mechanics, general relativity, information theory, thermodynamics, geometry. All of these great pillars of physics converge right here at this one fundamental scale. This convergence hints at a deep underlying unity. At the most fundamental level, reality might not be made of separate, distinct pieces. It might be one single, intricate structure that we are just seeing from different perspectives. What we call space, time, matter, and energy might just be shadows cast on the wall of our perception. Shadows from a deeper, more fundamental framework. The Planck length marks the spot where all those shadows overlap and merge. This perspective also changes how we think about knowledge itself. Knowing something doesn't always mean uncovering more and more detail. Sometimes, knowing means understanding why infinite detail can't exist in the first place. The universe isn't withholding information from us. It's telling us exactly how it works, and it's doing so with a quiet, profound elegance. As we move forward, we'll step back one last time and look at the full arc of this incredible idea. We'll trace its path from the smallest possible length to the largest questions of our existence. And we will ask a final, crucial question. Why does this discovery, now more than a century old, still matter so deeply to us today? Thank you for watching. When we zoom out from the Planck length and look at the universe as a whole, something remarkable becomes clear. The smallest possible scale is not isolated. It quietly influences the largest questions humans have ever asked. Questions about our origin, questions about our destiny, questions about meaning. The deeper we go, the more physics starts to resemble philosophy, not because it becomes vague, but because it becomes foundational. The Planck length forces us to confront the very nature of explanation itself. Why does the universe have laws at all? Why are those laws stable? Why is reality structured rather than just chaotic? At our everyday scales, these questions feel abstract, maybe even a little pointless. But at the Planck scale, they become unavoidable. If spacetime, matter, and energy all emerge from something deeper, then that deeper structure isn't just another layer of particles. It's the framework that makes existence possible in the first place. This suggests that the universe isn't just a collection of objects. It's a process governed by very specific constraints. The Planck length is one of those fundamental constraints. It sets a limit on division. It sets a limit on precision. It sets a limit on what it even means to ask where and when. Random fluctuations would grow without any bound. Geometry would collapse in on itself. Nothing lasting could ever form. It's precisely because there is a smallest scale that larger scales can exist. Stars can burn steadily for billions of years. Atoms can remain stable, allowing for chemistry. And life can evolve slowly over eons. The quiet calmness of the night sky depends on the strictness of these smallest rules. This connection between the extremes, the very small and the very large, is one of the deepest and most beautiful themes in all of physics. The smallest details shape the grandest structures. The quietest rules enable the loudest phenomena. Galaxies trace their origins back to tiny quantum fluctuations in the early universe. The cosmic structure we see all around us reflects a fundamental microscopic uncertainty. The sheer vastness of space emerges from the fact that reality has a finite resolution at its core. This isn't just some poetic metaphor. It's literally how it works. The universe is large because it is constrained. This idea also completely reframes humanity's role in the cosmos. We are often told that humans are insignificant because the universe is so incredibly large. But scale alone does not determine significance. Structure does. A universe that is capable of forming observers, beings who can look back and ponder it, all is already remarkable. A universe governed by precise, stable laws is extraordinary, and a universe with a smallest length, a fundamental pixel size that enables complexity to arise at all scales, is a concept so rare and so profound in its consequences. You exist because the universe has limits. Think about that for a second. Without a smallest length, reality would dissolve into pure instability. Without stable physical constants, time would have no rhythm, no forward direction. Without coherence at the deepest, most fundamental level, nothing could persist long enough to matter. In this sense, the Planck length isn't some distant, abstract concept that only physicists care about. It is present in every single moment of your life. Every breath you take, every thought you have, every memory you form. All of these are supported by complex biological and chemical structures that depend on physics behaving properly at the smallest possible scale. This perspective doesn't make life feel mechanical or predetermined. It makes it feel delicate, precious. Our existence isn't guaranteed by chaos. It's sustained by an intricate, fine-tuned balance. The Planck length is a crucial part of that balance. It reminds us that reality is not infinitely malleable. It has a shape, it has a texture, it has boundaries. And it is within those boundaries that all the richness and wonder of the cosmos unfolds. So, as we've journeyed from the absolute limit of smallness to the grandest questions of existence, we've seen how the Planck length isn't just a number. It's a key to understanding why anything exists at all. It hints at a deeper layer of reality, a quantum foam where geometry itself is born. This tiny, almost unimaginable scale underpins everything. It ensures the stability of matter, allowing atoms to form and stars to shine. It dictates the very fabric of spacetime, preventing the universe from collapsing into a black hole at every point. It's the silent foundation upon which the entire cosmic structure is built, from the smallest particle to the largest galaxy cluster. The universe is not a random collection of stuff. It's an ordered, structured process. And the Planck length is one of its most important rules. It forces us to accept that there are questions we might not be able to answer with our current tools. Not because we aren't clever enough, but because the questions themselves might not make sense at that level. Asking what happened before the Big Bang, or what S inside an electron might be like asking what S north of the North Pole. The concepts themselves lose their meaning. It means there are new ways of thinking, new forms of logic waiting to be discovered. The quest to understand the Planck scale is the quest to find a theory of everything, a single framework that unites quantum mechanics and general relativity. This is the holy grail of modern physics. It's a journey that takes us to the edge of human knowledge, pushing the boundaries of both technology and imagination. It reveals a cosmos that is not just vast and old, but also intricate, structured, and deeply interconnected. The smallest length is not a wall, but a window into the true nature of reality. Thank you so much for watching. If you found this journey as fascinating as I did, consider subscribing for more explorations into the biggest ideas in science. Until next time, stay curious. Just keep dividing, smaller and smaller, forever. But as we've discovered in modern physics, the universe has other plans. The answer to this question leads us not to an infinitely small point, but to a fundamental limit, a boundary that redefines our understanding of reality itself. This isn't just about numbers and equations. It's about reaching the very edge of what it means to describe our world. This ultimate limit is known as the Planck length, and it's not just small, it's staggeringly, incomprehensibly small. To give you some perspective, if you were to scale up an atom to the size of the known universe, the Planck length would be about the height of a single tree. It's the scale at which our familiar, intuitive concepts of space and time simply stop working. They lose their authority. Below the Planck length, the smooth fabric of spacetime we imagine dissolves into a chaotic quantum foam. Geometry as we know it breaks down. The very act of measurement becomes meaningless. Our descriptive language has to change. But here's the most profound part. At this mind-bending scale, nothing actually breaks. Reality doesn't collapse into nonsense. It just transitions. The universe doesn't become a storm of chaos at its smallest level. It becomes incredibly subtle. It's like looking at a digital image. From a distance, it's a smooth, continuous picture. But as you zoom in closer and closer, you eventually see the individual pixels. The image doesn't fall apart. You just realize it's built from discrete units. The Planck length is like the universe's pixel size. What appears unstable and random from our large-scale perspective is actually structured and ordered by a deeper set of rules. This limit, the Planck length, isn't a barrier that stops us. It's a foundational rule that allows everything else to exist. Think about it. Because there is a smallest possible distance, the fabric of spacetime remains coherent and doesn't tear itself apart. Because there is a smallest unit of time, the Planck time, the principle of cause and effect remains meaningful. One event can reliably lead to another. Because there's a limit to how finely you can divide things, structure can emerge and persist. Without this fundamental resolution, the universe would be an undefined, blurry mess. From this single, elegant foundation, everything we see and experience emerges. The elementary particles that make up matter, the fields that carry forces across vast distances, the atoms that combine to form molecules, stars, and galaxies, and ultimately, life itself. Nothing in your daily experience is separate. You are not some external observer looking in on the universe. You are a direct expression of it. You are made of the same stuff, governed by the same rules. The quiet, hidden rules that limit measurement are the same ones that enable meaning and existence. This realization doesn't make the universe feel smaller or more restrictive. It deepens it. It fills it with a sense of profound coherence. It reminds us that true understanding isn't about chasing after infinity or wrestling with endless paradoxes. It's about recognizing the intricate, interwoven patterns that connect everything. It's about seeing how immense richness and complexity can arise from the simplest of principles. The Planck length starts as a technical constant in a physicist's equation, but the more you contemplate it, the more it transforms into a philosophical boundary. It's a gateway to a new way of seeing the world. It tells us that reality is not an infinitely smooth, continuous canvas. It has a texture, it has a grain, it has a fundamental resolution. And within that finite resolution, the entire magnificent story of the cosmos unfolds. Every particle interaction, every chemical reaction, every thought that crosses your mind, it's all happening on this pixelated stage. The universe, it turns out, is not an analog recording. It's digital. And the resolution is incredibly, exquisitely fine. As you sit with these ideas, let them settle. Consider that every single moment of your existence, from the mundane to the magnificent, occurs within a universe governed by this quiet, unshakable precision. It's the smallest, most fundamental rules that hold the largest, most majestic structures in place. The delicate dance of galaxies across billions of light years is underpinned by a limit you could never, ever see. This isn't a fact to be intimidated by. It's something to appreciate, to feel a sense of awe about. The universe is not indifferent or random in its design. It is consistent, and that consistency is the bedrock upon which anything and everything is built. It's what allows for stability, for predictability, for the emergence of order from chaos. It's what allows for us. Thank you for taking this slow, contemplative journey with me to the very smallest scale of reality. It's a place that challenges our intuition but rewards us with a deeper sense of connection to the cosmos. If this exploration brought you a moment of calm, a spark of curiosity, or a new perspective, then our journey was a success. You are always welcome to return here to ponder these mysteries. The universe will still be here, quiet, structured, and endlessly patient. Thanks for watching.